Okay, so our last chapter that we're going to deal with for this test is chapter 32, which is called Maxwell's equations. These are four very, very, very important equations. There are actually many of them are come up with on their separately from one another, but Maxwell's really the one who unified them and did the final tweaking, and also realized what that implication was, and that this is really all sort of one big force. So these are four equations that encompass the electric field and the magnetic field, and then the charged particles and currents that produce them and that are also affected by them. And so this is a very complicated force. Mathematically, it's not as easy to write down as gravity, although the real gravity, which is Newton's version of gravity, is really an approximation of the actual gravitational force, which is also pretty ugly, actually. All right, so another story. Maxwell's equations can be written in either integral or derivative form. Just like you can write anything, calculus can be written in either an integral form, right? So we could say that the velocity is the derivative of position with respect to time. That's a derivative form. But we could also say the change in position is the integral of velocity dt. And so anything can be written, or calculus kinds of things can be written in integral or derivative form. It's actually, although we think of integration as being a little more complicated than derivatives in physics 111 and 112, when you have three-dimensional derivatives and things like that, Maxwell's equations actually look better and are more easily understood in the integral form at this level. And that's what we've actually been looking at. We've actually already done 2 of the 4 equations. So in chapter 23, the first one we came across was Gauss's law for electric fields. We had all these problems where we had stuff that looked like this, where we had, shells of things around point charges, and we said that this was true, that the closed surface integral of the electric field along some area of that surface was the net electric flux, and that was equal to the charge which is enclosed over this constant epsilon naught. This is Gauss's law for electric fields. It's an extremely important it's the first of Maxwell's equations. And I think hopefully these questions, we're not going to do any more of these, but that is the first one. The second one that we've really already completely covered, although it's usually written as the third one down when we do it, is what we just did in chapter 30, Faraday's and Lenz's law, where most of the time when we were doing Faraday's and Lenz's law, it actually looked like this, where we said we have a loop of wire, and if we have a loop of wire, and in a region where the magnetic flux is changing, right? If I've got my loop of wire here, and I've got a magnetic field which is going in like this, and let's say that magnetic field is decreasing, then I'd get this current that would form in my thing. If it's decreasing, then I'd expect that the loop itself would make a magnetic field, which is also into the board or into my screen, and so I'd expect a current that would go like this. So I have an initial magnetic field, my external magnetic field, and then I would have a second magnetic field, which is coming from the current, which is also moving inside, right? So that's what we've sort of mostly did. But we did do, I'm going to do on Monday some examples of this, and there's also some recorded versions of lectures. I think it was the part 3 of chapter 30, where I show that even if you don't have the loop of wire here, say there's no loop of wire here, and so we don't get a second magnetic field, even if there's not a loop of wire, if I have a decreasing magnetic field going in, what I'm going to produce is I'm going to make an electric field. The electric field is going to be circular like this, and the direction of the electric field is going to be in the direction of that current. And so I get an electric field because I have a changing magnetic field. What Faraday's and Lenz's law really says, and when we write it out according to in Maxwell's equations point of view, is it's written like this. And what that equation says is that a changing magnetic field creates an electric field. If you have a changing magnetic field, you're going to make an electric field, and a weird electric field, this weird sort of, loopy electric field like this. It's not a linear electric field. You get this strange circular electric field. Or it doesn't have to be circular, but something like in that sense. And so this is really a big thing, especially when we take it with one of Maxwell's equations. The third one we've done part of. So we had Ampere's law. So there's an Ampere's law we saw back in chapter 29, and we used Ampere's law to determine all kinds of things like this. But Ampere's law essentially says that if you have current, it's going to create a magnetic field, right? So if we had a straight wire, with current, then we could say, okay, well, at some location away from that, right here, there's going to be a magnetic field at that location. And if I did my right-hand rule 2 here, I'd say, well, at that location, I'm going to get a magnetic field which is going into the screen, right? If I've got current moving like this. And then above it, I'd have magnetic field coming out of it. And Ampere's law is the one who tells us, how to get the actual equation for that. And it basically was saying that the magnetic field along some closed path, in this case a circle with radius circumference 2 pi r, is equal to mu naught times the current. And so here's this equation from Ampere's law would be this would say B 2 pi r is mu naught I. And that's where that came from. But we didn't see this other term. So this is the Ampere's law part here. But the actual equation has an addition that Maxwell put on. So Maxwell had this addition to this thing. And in chapter 29, by the way, this is also a problem we used back in chapter 29 when we used Ampere's law. Maxwell adds this other term. He says this. And this is a situation where our electric flux might be changing with time. The electric flux is, again, it's how much electric field goes through a certain area. And so if you've got a changing electric field, or for some reason you had a changing area that changes with time, then you might get an additional magnetic field. More magnetic field is going to be produced. So let's think about just an RC circuit. So if I have this RC circuit where I have some EMF and I have a resistor and a capacitor and I have some switch, when I first close this switch, all right, close the switch, and then what's going to happen is I'm going to see current start to flow like this, right? Current's going to come, it's going to go through my resistor, and it's going to come down here to my capacitor. If I have current coming out of my EMF, I've got to have current coming into my EMF, and so I've got current going like this. And so we always show the current is flowing around our circuit. And it's going to do that. It's going to flow until the capacitor is fully charged, where the Q on the capacitor. So I'm going to build up a positive Q on this side and a negative Q on that side. And that's going to be our Q max, which is the capacitance times the EMF. It takes a while. This was basically the RC circuit you guys built. But when we do that, we've got this blue thing saying that the current's going around it, but is current really flowing through my capacitor? is it really, I mean, is current flowing through the capacitor? Right? The capacitor are two metal plates which are separated from each other by air in between them, or sometimes things that are worse than air. No, current does not flow. Current cannot flow across from one side over here to the other side. It can't do that. But in that region, as we build up more and more charge on the plates, as you build up more and more charge on these plates, I am getting an electric field. I am building an electric field, and I'm building a stronger and stronger electric field as time goes by. So in this region, this electric field is getting stronger as this flows. And so my electric flux is becoming larger. In this region, my electric flux is basically just the strength of my electric field times the area, and then it's also, I guess there's a cosine of the angle here between them, but in this case the theta is actually 0 degrees. And so the changing electric flux with time, which is what's in this equation that he put in, he said the changing electric flux with time, it's just going to be the area times the change in the electric field with time. This idea of if you multiply the changing electric flux with time times the constant epsilon naught that we had way back in our very first chapter, you get units of amps, you get units of current. And so Maxwell called this the displacement current. And I have it drawn as a dashed line here. I have it dashed as a dashed line because it's not real. There's not an actual current there. There's a real current that gets basically is delivering, if we pretend it's positive charges are the things that move, it's delivering positive charges to the top plate from the positive of the EMF. There's a current moving away from the negative plate, which is removing positive charges from that side towards the EMF. But in between, we don't have real current, but what we do have is an increasing electric field. And so that's sometimes called the displacement current. It's not a real current. It's a fake current. But just like an actual current, so this current right here, according to right-hand rule 2, would make a magnetic field like this around itself. If I do right-hand rule 2, my fingers would go into the board, into the screen on this side, and they'd come out on that side. Up here, the same thing. I get a magnetic field, which looks like this. Inside the capacitor, I'm also getting this. Around the capacitor, I am also producing this magnetic field like this. I'm essentially producing a circular magnetic field in that location. Let's see if it actually can show us. I think there's some pictures which are nice for this. Oh, no, everyone can't find them. Maybe they're here. Yeah. So again, here's our capacitor, and they're showing us even inside this capacitor what this would look like, these circular magnetic fields that are existing inside our capacitor. So just like the actual current creates a magnetic field using this equation around the wire. This fake current, or it's actually the fact that we have a changing electric field, it also produces a magnetic field around the capacitor. You don't have to have current. You can have a changing electric field and it will produce the magnetic field. And so a changing electric field creates a magnetic field. That's what Maxwell's addition to this law says. He says that if you have a changing electric field, you'll get a magnetic field. But we also just saw in Faraday's or Lenz's law that a changing magnetic field creates an electrical field. This becomes a cyclical effect. If you have a changing magnetic field and that produces a changing electric field, that changing electric field will then double back and produce the changing magnetic field. This is really where Maxwell has his breakthrough, and we really talk about it in chapter 33 briefly. For number 13, which is using a capacitor, where very specific stuff. So in a capacitor, the electric field magnitude is the voltage across the capacitor divided by the separation and distance between the two plates. Putting all that into this displacement thing. So again, the displacement current is epsilon naught times the time derivative of the electric flux. And then that is just the area, the E naught, epsilon naught times the area times the change in the electric field, right? That's this guy I've just substituted in. And then if we know the electric field is the voltage divided by the distance, we can actually put this in. And so what I end up with is that the displacement current for a capacitor is the capacitance times the time derivative of the voltage. So number 13 says, at what rate must the potential difference between the plates of the parallel plate capacitor change? So it's asking us for this. What does that have to be if we want to get a displacement current of 1.5 amps and we've got a capacitor which is 2 microfarads. And so we're going to use this equation, C dV dt, and we're going to solve for dV dt, which is just the displacement current decided by the capacitance. Okay, when I do that, it has to change by basically a huge amount, 7.5 times 10 to the 5 volts per second. So that's a very large drop in or change in voltage across your capacitor to get a displacement current of 1.5 amps. All right, the last equation of Maxwell's equations is actually Gauss's law for magnetism. So comparing this to our first one, which was Gauss's law for electricity or electric fields, where again we would have, we say the closed surface around some charge distribution, the flux that's going to come out of that is just going to be how much charge is in there over some constant. For magnets, again, we have the magnetic flux, the net magnetic flux here through a closed surface. But here it's equal to 0. So if this was really normal, we would sit there and we'd say, is there some magnetic, pole inside there by itself? But this rule actually says, it says that the net magnetic flux through some closed surface is 0. It says that the magnetic field lines that go into this closed surface have to equal the magnetic field lines that come out. And so they've drawn for us two surfaces here, our surface 1 and then surface 2. And if we went through and we counted how many lines come in down here, and then we counted how many lines went out up here, they would be equal. And the same with this smaller surface. We have 3 coming in and we have 3 going out. The only way you got electric field lines to have more field lines coming out, say, than you had going in is if you had a positive charge inside. Or if you had a negative charge inside, you'd have more going in than you have coming out. So what this really tells us, Gauss's law for magnetism says that there are no magnetic monopoles There are no north poles that exist without also having a south pole. If you took a bar magnet that was like this and you cut it in half, so now you have two bar magnets, and you have this side and you have this side, all of a sudden this would become a south and this would become a north. You can't just get a north end of a magnet. If you cut a magnet in half, now you have two magnets which are shorter than you had before. So you can't have a magnetic monopole. Number 3, I may see if we have time to do this one in class just because I don't want this to be particularly long. But this is the same. We have basically an idea here. So it tells me I have a Gaussian in the shape of a cylinder where the end caps, where the whole thing has got a radius of 12 centimeters, right? From here to here is 12 centimeters. And the length of the whole thing is 80 centimeters. And it tells me at one end, which I decided to be the right side over here, I have a flux of 25 microwebers going into it. So because it's into it, that flux is officially negative. It tells me at the other end, I have a certain magnetic field which is coming out. Now that's the magnetic field. The actual flux at that end should be the magnetic field times the area, which is this area, right? So our area is just the pi r squared. And then the area vector is also out, and so our angle here is 0. And so I can get the magnetic flux that's coming out at the other end. And then the problem actually wants to know what's the magnetic flux from the curved section. Well, the magnetic flux from the curved section plus the magnetic flux on the right-hand side and the right-hand flux on the left-hand side, they all have to add up to be equal to 0. And so we can use that to determine the magnetic flux on the curved section. Doing some fairly simple steps. All right, that's all for this week. It's a lot. Hopefully we'll have time to cover most of this in class as well.